a historic event because it involves this guy, Albert Einstein. I'm going to take you through the history of why this particular eclipse was so important to his development as a scientist and the emergence of his theory of gravity, which has, in spite of what was reported back then, his theory has practical applications, which we will discuss later this evening. So I just want to point out that this version of the lecture is derived from a version that I gave on a cruise ship, the Azamara Quest, whoops, because there was an eclipse, an annular eclipse back in December, actually the day after Christmas of 2019. And I was on the cruise ship to lecture about eclipses and their history and so forth. So I've made some improvements to this, including a little description of an eclipse of this type that happened just 3 days ago.
Right.
So we'll talk about that. So once again, here's the list of upcoming talks. I'll leave that there for a second if you want to take a screenshot or capture that with your camera. Okay, so the focus of what we're going to talk about revolves around Einstein's plan for developing a theory of gravity. And it took him over 20 years to do this. Along the way, he produced some astonishing science, not just in the theory of gravity, also called the theory of general relativity. And we'll cover that. And I'm going to show you some technical, there's no equations, but I do want you to understand the techniques used for him to prove his theory. Now, there's a difference between crackpot science and real science, and the difference is that real science makes predictions. Crackpot science, which is all around us, makes assertions without proof. Einstein's theories made predictions, and we're going to go through the sequence of those just so you can see the range of things he covered in his work. And in the process, we'll see the results of his predictions. I'm going to make a statement now that I'll probably come back to, and that is, over the last 100 years, literally billions of dollars have been spent to make sure that his theory is right, and there's so far no contradictions. A lot of that money has been spent in the last 25 or so years flying space missions to detect the effects of the theory of general relativity, also called the theory of gravity. And he was right. So now, he didn't do this alone. He was very fortunate that as his conceptual understanding of gravity evolved, he had close friends who assisted him passively in one case and actively in one case. Without those people, he would have struggled because the mathematics involved in the theory of gravity is extremely complicated. And Einstein was not a master of the topic. I'm going to show you who was, but he had friends in the right place to develop the theory. He also had this guy, Arthur Eddington, who was the most prominent scientist of his day back in the early 20th century. Eddington, an Englishman, was very prominent, and as the story unfolds, you'll see what his role was. He also had these acquaintances. Most important, on the left, Marcel Grossman, who was a mathematician friend of Einstein's, and Grossman made a considerable contribution to Einstein's theory because Grossman understood the math. For those technical people on the call, the topic that Grossman understood and was needed by Einstein is called differential geometry. It's a field of math that did not exist until about the 1870s. And without it, we never get to Einstein's mature theory. And then, of course, there's a picture of Einstein as a young man. And on the right side is his friend Besso. And Besso is the person I mentioned who was a sort of a passive participant. Besso was a close friend of Einstein's and was his foil. When Einstein tried to develop his theory, he did many, many thought experiments where he tried to describe to himself and then to others how he understood the way nature works when you're talking about gravity and why Newton's law of gravity, which we all encountered in high school physics, why that was the right law, but Newton never explained why it was the right law, and it was Einstein's passion to understand that. Besso was a correspondent of Einstein's. They had many letters going back and forth where Einstein attempted to explain verbally and in writing how his ideas were emerging. And Besso, who was not nearly the intellect of Einstein, kept asking him basic questions. And it is true of all the sciences, if you can't explain what you're doing in simple terms, you don't understand what you're doing. And so Einstein was challenged by Besso to develop his theory in a way that was understandable. And so Besso played an important role as a correspondent. So we also had near him, not initially known to him, people who watched his theory evolving and got excited about proving or disproving these ideas that he was creating about his theory of relativity. Maybe we can get somebody to mute their dog. It's kind of distracting me a little bit. Unmute me. The most eager of the people who wanted to prove or disprove Einstein's theory of gravity was Freundlich, shown here. Freundlich was at the time, this is a picture of Freundlich near the end of his career in the early 50s, but at the time, we're talking about the interval between 1905 and 1920, Freundlich was trying to make his name as an astronomer and was very excited when he saw Einstein's theory, and he said, I think I know how to prove whether Einstein is right. So Freundlich plays an important role, as we shall see. Now, there are a couple of different things where Einstein made predictions from his theory. One that we will talk about quite a bit is to measure the apparent position of stars when they are near the sun in the sky. So we have to have some clarity here. You can't, if you go outside on a sunny day and try to look for stars, of course, you're not going to see any because the sun is way too bright. But during an eclipse, the sun is blocked out by the moon, and those stars that are close to the edge of the disk of the sun can be seen. Many of you probably witnessed the eclipse here in North America in 2017, where it got dark and you could see stars. I took some of my grandsons, we went up, I live in Denver, we went up to Wyoming. We were on the path of the eclipse and it got mighty dark. Curiously, people around us kept complaining, how come it's not getting dark? And I had to point out to them that all the street lights are on. The technology notices that it is dark your eyes have expanded to accommodate the fact that the sun is blocked out. So it gets dark and you can see the stars, and Freundlich understood that and was interested in finding an appropriate eclipse where observations could be made to see if the apparent position of the stars changed in a way predicted by Einstein's theory. And I will get into that in a little bit more in a second. So you need a total solar eclipse to do this kind of measurement. And it has to occur at a time and place where there are a large number of stars in the vicinity of the sun. And also important, the disk of the moon has to completely cover the disk of the sun. That does not always happen in an eclipse. Actually, as I said, 3 days ago, we had an eclipse occurred. It was visible in India, from Africa to India, and it was an annular eclipse. And we'll go into detail here in a second about why sometimes the moon covers the entire disk of the sun and why other times it does not. So Freundlich was interested in finding an example of an eclipse where the moon was going to completely cover the disk of the sun and where there would be a dense background of stars where photographs could be made of the positions of those stars, and those photographs could be compared with pictures of the dark sky, the pictures taken at night of the same group of stars, because Einstein's theory predicted that the positions of the stars would be affected by the mass of the sun. So from his calculations, he went through the laborious work predicting where the stars would appear. And there's some drama there. We'll get to that. So if you're planning an eclipse adventure, you have to have good weather. You have to have the right equipment. You got to be in the right place at the right time. Your equipment has to work, and you got to be able to raise some money. This is always an issue with doing science. And nothing else can get in the way. And I leave you to think about what I'm about to explain. I'll leave you with that little teaser. Nothing else can get in the way. Well, okay. So all these things have to cooperate if you're going to have a successful observation of stars during a total eclipse. So let's talk a little bit about Einstein's theory. This is generally considered to be the greatest achievement of the intellect of man. As I say, it took about 20 years for Einstein to bring his full theory forward. We know of no case where it's been disproven. And his concept was that Newton's law of gravity, which is easy to describe with a simple equation, has an underlying reason why two bodies are attracted, the so-called gravitational effect. It's the reason that you and I are not floating out into space. Earth is tugging on us, and the question is why? And Einstein's interpretation was that the presence of the mass of our planet distorts what he called the space-time continuum. That the presence of a mass or any form of energy changes the shape of space and the progress of time. And these topics we will discuss as we continue our adventure. Before inventing his theory of gravity, he had invented something called the theory of special relativity, which is taught at the high school level now. And it does not include the effects of gravity, but it provides the student or the participant with the foundations needed to understand the theory of gravity. And part of that, the most important part, is that the speed of light is the same for all observers. From that simple concept, Einstein thought about his ideas about gravity. He, as I say, wrote many letters to Bessel and tried to explain it in terms that a non-scientist could understand. And during this development of his ideas, he realized some fundamental things. One, the speed of light is the same for all observers. Second, he realized in a flash of insight that if you put an astronaut, of course the term didn't exist back in the early 1920s, but if you put an astronaut way out in deep space away from everything else, they're just floating. They have no sense of falling. They're just present in the universe. He realized that the experience of that astronaut is the same as someone who's in, for example, an elevator hung by a cable here on Earth, and somebody snips the cable. That falling in a gravitational field is the same as floating in deep space, far from any influence of a mass. And he used that to develop his theory and produce testable results. One testable result is that clocks close to a mass run slower than that same clock if positioned away from that mass. And we will see a practical application of that near the end of this talk. He also noted that light passing near a massive object is deflected, that the space-time continuum near a body like the sun changes the trajectory of light. I'll show you pictures of what we mean. He also calculated the influence of gravity near a large body on the orbit of for example, a planet orbiting the sun. That Newton's law for calculating trajectories was incomplete. Although we still use Newton's approach to fly to the planets to do science, a subtle difference exists between Newton's and Einstein's law, and Einstein calculated the impact of that. We'll talk about that. So first of all, this is kind of a visual of how Einstein was thinking. He says, if I take space-time, which would normally be a flat sheet here, think about a trampoline, for example, and I put onto the trampoline an object, the sun in the solar system, but you might think about put a bowling ball on a trampoline. The presence of the bowling ball distorts the elastic material, and if I roll a golf ball across that trampoline, it's not going to have a straight trajectory. It will be deflected because of the shape, the influence of the presence of this mass. And in fact, if you use Einstein's theory and go through the math, you can derive Newton's law of gravity, which is very comforting because Newton's law of gravity does explain the motions of the orbits of the planets and the moons and so forth. But Einstein's understanding was it's just not, gravity just doesn't exist on its own. In fact, he essentially proved there's no such thing as gravity. What we experience is distortion in the space-time around a massive object, and everything is affected by that. Clocks, objects that are moving, and so forth. So here's the trampoline I mentioned with a bowling ball and a golf ball. You've all seen this kind of thing happen. The fact that space-time is distorted also influences the trajectory of light, because the light encounters the same distorted space-time that an object like a planet encounters. So if we have a star over here observed from Earth, light traveling near the sun, if that light is passing close to the disk of the sun, its trajectory is altered. And you have to think about this a little bit in reverse. When we see something with our eye or a telescope, we perceive its position as if a straight line exists between how that light entered our eye and where the object actually is. So if the light from the star is distorted on its path and encounters a telescope or our eye, we don't see the star here. We see as if it was here. And so the presence of the sun makes this star appear in another place. And this is the foundation for the idea that this theory could be tested using an eclipse. A star that's farther away from the sun, where its trajectory does not come close to this area where there's a significant distortion in space-time, that light ray is deflected very little. So it's this effect that Freundlich and others wanted to detect. And the only time you can see the light from this star passing near the disk of the sun is if there's an eclipse going on and we're not blinded by the sunlight. I also mentioned that Einstein's theory predicts distortions of orbits. And here's a cartoon example of what he was thinking about. The orbit of Mercury, being the closest planet to the sun, feels the effect of this distortion of space and time induced by the sun. And for the period from probably the 1840s until Einstein was active in the early 1900s, people had measured the orbit of Mercury and tried to equate its orbit with Newton's theory of gravity, and there was a difference. It's a tiny difference, but they noticed a difference that the orbit is not predicted by Newton's theory. So one of the first things Einstein calculated after his theory was mature was, how is the orbit of Mercury affected? And the orbit has this kind of spiral effect. It works its way around, and the rate at which the orbit moves is called the precession of the perihelion. That is how the orbit changes relative to the sun. And one of the first successes of Einstein's theory was he was able to calculate exactly the observed orbit of Mercury. This was a huge success. And in his circle, he became immediately famous. Now, you have to understand that we're talking about a time when science was a tiny part of society, and news about science was slow to progress. So the circle of friends that Einstein had included probably 25 people who were shocked that he was able to properly calculate the orbit of Mercury. This to him was a huge achievement. But our focus tonight is on eclipses. So by 1911, Einstein, well, first of all, a little chronology. 1905, he produced his theory of relativity, special theory of relativity. And then he set to work on his general theory. Along the way, he also produced two other very significant results, also in 1905, one of which led to his Nobel Prize in the early 1920s. Ironically, he was never formally awarded a Nobel Prize for relativity. There were some issues with German scientists who felt like any product of a Jewish scientist had to be held in disregard. But let's get back to our story. By 1911, Einstein had predicted the orbit of Mercury. And for him, this is, I actually have a quote here, that he was, well, here it is. He was beside himself with joyous excitement.
Oh, cool.
So those of you who are interested in doing more, there's references at the end of these lecture notes. Some of you may have seen the movie Interstellar, written or produced by Kip Thorne, who is the most prominent gravitational scientist alive today. he has a book about how the science for the movie was developed. It's not a science fiction movie. There are parts of the science in the movie that are speculative, but it is not like Star Wars, where you have tractor beams or things going faster than the speed of light. Anyway, there's if you want to read more about this topic in a non-technical way, this is a great book to look at as a companion to the movie. So let's talk about eclipses now. In 1913, by 1913, Einstein had predicted the deflection of starlight from his theory. He got very lucky because his first calculation was wrong. He did not know this until some years later. And for reasons you shall see, he got extremely lucky because early plans to test the theory with eclipses would have revealed the defect in his theory, and his sudden emergence as a prominent scientist would have been derailed. In fact, here's a letter dated 1913 with this cartoon showing something like the picture I showed a few slides ago, deflection of sunlight passing near the disk of the sun. And actually, here's the same letter in English where he calculates this number, 0.84, and it looks like a quote mark. That means arc seconds. Arc second is a very tiny fraction of an angle. It's 1/3600th of a degree. And so he had calculated that the deflection of starlight passing very close to the disk of the sun would be seen in compared to a nighttime photograph of the same stars as just a bit smaller than an arc second. And this prediction was shared amongst his colleagues, including Freundlich, who wanted to do experiments using eclipses. So here's what Freundlich was thinking about. Here's the sun, here's Earth, and in this orientation, this side of Earth is sunlit, the other side is dark. And this is the situation we have if you're here you're looking at the night sky and you see these stars. Now what we could do is wait, if not necessarily 6 months, but this is where Earth would be 6 months later. And now this side of the Earth is sunlit, but if the moon gets in the way, we can look at those same stars and the rays of light have to pass near the sun and would be deflected. More deflection if those spots of light are close to the disk of the sun. But you can only do this experiment during an eclipse. So astronomers had regularly taken photographs on glass plates, was the technology of the day. And they had huge archives of pictures taken at night. I mean, this had been going on since the invention of photography. And in fact, before that, it was done by drawing pictures. So there was a large catalog of photographs of the night sky, and there were even photographs of eclipses of the areas of the sky. And Freundlich wanted to take advantage of those previous things. I am going to skip this slide. By the way, I do want to show this. If you take this piece, it looks like a piece of modern art, and paste it on the wall and then put a black hole in your room between you and this piece of art, this is what you see. Tremendous distortion. Here's another example, and this actually comes from Kip Thorne's book, where if you had a disk of light out in the distance and you put a black hole in the middle of the disk, you see these big distortions. Of course, Einstein and his colleagues were looking for much smaller effects and made it much more challenging. Now, I've also included these images because these are photographs taken from the Hubble Space Telescope and other astronomical systems where this arc is a single galaxy in the distance, and in between us and the galaxy, there's a large massive object, probably a very compact galaxy that bends the light. And so all this light is coming from a small spot similar to this, but it gets stretched and distorted based on the kind of thinking that Einstein had in mind. In fact, you can see it here in these pictures. Arcs, anything that's arc-like, these smiles, those are the result of light being bent on its way to us, and that light has passed near a massive object. So the question is, was Einstein's theory right in calculating the amount of distortion? And here we come to a phenomenal curiosity about our solar system, and that is, this is why this asterisk is here. To do this work, the size of the moon, the apparent size of the moon, has to be just right so that it covers the disk of the sun and doesn't allow any sunlight to leak around the edges. And the fact that our moon has just exactly the right size to do this is a complete coincidence. There's nothing in astrophysics that dictates that the moon should have the same apparent size as the sun. And in fact, there's a little wrinkle to this that we will talk about. But it turns out in 1919, the eclipse we're talking about, the eclipse was of the right type. That is, the moon was in its orbit in the right place to cover the disk of the sun, and there were plenty of background stars. But there was an eclipse before the 1919 one, 1914, where Freundlich and others went to look for an eclipse to prove or disprove Einstein's theory. As I mentioned, Einstein had written a letter in 1913, actually had also produced a calculation in 1911 predicting the amount of deflection that should be observed. And his result was exactly the same as what you get from using Newton's law of gravity. So at this point, Einstein did not realize that his first calculation was incorrect, and he predicted this number. This is the one that appears in his letter. And Freundlich, I'm just emphasizing that the fact that the moon obscures the sun during a solar eclipse is a complete coincidence. So Freundlich went looking for this deflection in 1914. And well, let's see, most of this, I've said all this. Now, this is an interesting picture. This is an example of the eclipse photography that had been done prior to Einstein's theory. This dates back to 1900. The circles indicate the positions of stars. There's the disk of the sun obscured by the moon. And if you had access to the original plate and looking closely at it, you'd see a little black dot. This is a negative. So you'd see a little black dot inside each of these circles indicating the positions of stars. This one right here would have been a good candidate to test Einstein's theory. I mentioned that the deflection would be about 1 arc second. That's a tiny angle. It's about the spacing between the headlights of a car, if you view that car, from a distance of about 300 miles. So we're looking for a tiny effect. And so Freundlich had seen Einstein's theory, had been in correspondence with Einstein, and said, I'm going to raise money and we're going to do an experiment and prove your theory right or wrong. Freundlich also obtained plates, photographic plates, mostly from the United States, of earlier eclipses in an attempt to detect the effect. But those pictures just weren't done in the right way to allow this kind of sensitivity. And he had been traveling around, as you see a list here of different places, he had been trying to find eclipses from the past record that could be used, but that just didn't work out. He also was very vocal in the astronomy community, which was very tiny at the time. And he attracted the attention of Willem de Sitter, a Dutch astronomer of prominence. He got de Sitter involved, and Eddington, I've already mentioned, the most famous scientist of his day. And they got very excited about testing Einstein's theory. In fact, de Sitter was so famous that he was the subject of an editorial cartoon. This dates from 1930, I think. Yes, 1930. People who with a background in physics or astrophysics will notice that his body is in the shape of lambda, the Greek letter that has some significance in this field. So Freundlich had this kind of technology. You can see here, gives you a sense of scale. These were telescopes designed to do ecliptic astronomy. And it's a big deal to move this and set it up and hope that you have good weather and so forth. So lots of challenges in building one of these, aligning it, making it portable and so forth. So 1914, there was going to be an eclipse of the right type, relatively close to Europe in the Crimea. And Freundlich set off with a team right on the verge of World War I. And things did not go well. Because when he arrived, the Russians, you might have seen this in the newspaper recently, the Russians are in Crimea. And Freundlich was arrested. His equipment was confiscated because they thought it was military in nature. Meanwhile, William Campbell, an American, was trying the same thing. He picked a spot. Now remember, you're doing this eclipse thing. The eclipse doesn't last all day. It lasts for a matter of maybe a minute or a minute and a half. So Campbell was somewhere else nearby in Crimea, trying to take pictures for, once again, to confirm Einstein's theory. And he was not interfered with by the Russians, but he had cloudy weather. So no pictures from there. And had they made successful measurements in 1914, they would not have gotten this number. They would have gotten a number twice as big, because Einstein, in his effort to developing his theory, missed a 2 in his calculations. This was not detected for years. So he would have been embarrassed and would have had some real issues. Yeah, it was 1915 before he realized his problem. So here's an example of the telescope complex that Freundlich had in mind in 1914. And it looks like a mortar or something. You know, it's not hard to understand why somebody would want this confiscated. Eddington, meanwhile, was plotting to do a real expedition in 1919. And here's the same kind of picture where here's the astronomer, here's the moon blocking out the sun. The true position of the star is here. It gets bent on its trajectory coming to the astronomer and appears to be here. So if you measured it at night, you would see it here, but during the daytime, you see it there. So Eddington had access to more funding than Freundlich and the others, and he had a scheme for dealing with the weather. He sent a team to Brazil, which was on the trajectory of the 1919 eclipse. And he took a different team to the little tiny island of Principe in the ocean next to Africa. And there was some concern. First of all, Eddington was a Quaker pacifist. The war had started. He was very concerned about getting drafted, but he had such a reputation in the British intelligentsia that they worked hard to convince the army not to hand him a rifle, but rather to allow him to continue to do science. So the war was on, but he sent his team to Brazil, and he took a team to Principe. And there's a paper available online that shows the results. It's about 30 pages. There's a link there if you want it. And Principe is inside this little box. It's right there. It's right off the coast of Equatorial Guinea. It's a tiny, tiny little island there. If you ever go there, you'll find a memorial to this whole adventure. So Eddington went to Principe and sent a separate team to Brazil. And he took, this is a photo from one of the plates taken during the eclipse of 1919. And here's the position of the star, a star. It's one of about 6 that were detected. Here's where that same star appeared in a nighttime photograph. So this distance from here to here was critical. Oh, and here's a photograph taken during the eclipse, May 29th, 1919, with solar prominences and so forth. And they were very fortunate also on Principe. They had cloudy weather, but it was like a tropical environment, and the clouds opened briefly, and then and right in the middle of the full effect of the eclipse. So I've already talked about what happens. Here's the disk of the sun in this cartoon. A star very close to the disk of the sun experiences the biggest effect because the light rays pass near this gravitational body. So this star appears here. A star farther away sees a little smaller effect, and it barely moves. So you want stars that are very close to the disk of the sun to be able to detect this effect. Here's a simulation that I made of the eclipse of 1919 using a piece of astronomical software called Stellarium, which I highly recommend. It's free. You can run it on all kinds of computers. And I set the clock to May 29th, 1919, and positioned myself on Principe. And this is what you see. All these stars. Oh, and the interesting thing about Stellarium, by the way, is as you let it flow forward in time, the disk of the moon appears and crosses the disk of the sun, and everything in the sky becomes visible. They have actually simulated how bright the sky is. So these stars right here were the ones that made the most available data in the photographs that Eddington took, particularly this one, because it's right on the edge of the disk of the.
That ball was traveling like 700 miles per hour compared to.
What's that? Oh, okay, I will keep going. So the results that Eddington got were in the newspaper by November of 1919, and Einstein immediately was famous. The data that Eddington collected was a little sparse, and people felt like, at least some critics felt like Eddington had bent over sideways to make sure that the data confirmed Einstein's theory. So their work was repeated in 1922. And instead of having 6 useful stars in the image, they had 128. This was the best data taken up until the 1950s. I'll show you the history, but here's what they got. Astronomers went through the 1922 eclipse in great detail, 128 stars, and they got an average deflection of 1.72. Now remember, Einstein originally predicted 0.87. He was off by a factor of 2. By the time 1922 had come around, he found the error in his math, and he predicted a number of 1.75.
Oh my goodness. That's great.
So 50 years went by and these results were repeated. I'm going to show you history here in a second. Here are the headlines. Einstein's theory was on the front page of magazines and newspapers. By the way, here's the trajectory of the eclipse. You see it passes through this coastal town in Brazil where they got more data, but it was some issue in alignment of their telescope. And there's the little island of Principe. Here's 3 headlines, one after the other, in the New York Times from November and December 1919. Now here's something that's very interesting. Physicists agree that this result can be disregarded. It's not practical. It means nothing. And I'm going to show you, before I'm done, I'll show you that that is not true. So the work has gone on about the deflection of light by a massive body. Now, it takes a minute to understand this graph. So this is the year from dating back to 1920 till 2015 or so. Any number that's close to 1 means it agrees with Einstein's theory. So back in the early 20th century, the error bars were quite large, and these red ones are all from optical telescopes. The green ones are exploiting radio telescope technology. And you can see here, remember this line, this horizontal line, represents the fact that Einstein is correct. And the latest radio telescope work on this topic tells us that he's exactly right. The error is so tiny you can not see it on this graph. Similarly, there's a different thing called the Shapiro delay. Same thing. Radio experiments from spacecraft have confirmed that Einstein's theory is exactly right. I've drawn these lines on to just show how the error bars have been progressing, and we're confined to this little area here, indicating that the theory is right on target. It turns out that these days, if you have a few $1,000s to spend, you can do the same experiment. This is Don Bruns, a picture taken in 2017 when we had the full eclipse in North America. And his numbers came in between 1.69 and 1.81, the average of which is just about what Einstein predicted. Here's an example of Don's pictures where he has the disk of the moon there and other technology to suppress the sunlight that gets in the way. Now, here's where my experience with the annular eclipse occurred. Back on the day after Christmas 6 months ago, I was invited to speak on the cruise that made this tour from Dubai, made some stops in the Arabian Peninsula, and then we were on our way to Mumbai, India. And here's the depiction of the path of the eclipse. Now, this is an annular eclipse, this one on December 26th, meaning that the moon did not completely cover the disk of the sun. I'll describe that in why in a second. And our ship, because of economics, the ship went directly from Muscat, Oman, to Mumbai, India, and we were somewhere in here when we witnessed our eclipse. And when you have one of these annular eclipses, the sun is visible, and you see these bright areas. These are caused by the moon, the mountains on the moon. In some places, the mountains stand up high enough to obscure the sun. In other places, they don't. So you see something called Bailey's beads in, let's see, so an annular eclipse looks like this. The moon doesn't quite cover the disk of the sun. So not all eclipses are equally useful in doing imaging for studying the theory of gravity. Now, why is it that sometimes the moon covers the sun and sometimes not? And it's because the moon's orbit is not a circle. It's a bit elliptical. So sometimes it's farther away from us and looks a little smaller, and sometimes it's closer and looks a little bigger. So I have this cartoon to illustrate. Now, the sun also has an elliptical orbit, but Earth's orbit around the sun is also elliptical, but it's nearly a circle. So the sun appears to get bigger and smaller through the year, but it only changes, the apparent size of the disk of the sun only changes by this little bit. The moon, on the other hand, changes from being this small to this big. Now, of course, the size of the moon isn't changing. It's the distance from the moon to us that causes it to appear bigger or smaller. The coincidence that we employ is indicated by these horizontal lines. When the moon is farther away, it's smaller than the disk of the sun. That's what this indicates. When it's closer, it can be bigger. And we don't want an eclipse where it's so big that it obscures stars that might be right on the edge of the sun, because those are the most important ones in making the measurements, because they experience the biggest gravitational deflection. So you want an eclipse where the moon's disk is just right on top of, but not obscuring much of the additional sides of the sun. So here's a little bit of technical data. Now, once again, this is a complete coincidence that the moon is just the right size to block out our sun. If it was dramatically smaller or much farther away, we would never have a useful eclipse for doing this kind of astronomy. If it was bigger or closer, when we had it, all eclipses would completely obscure the sun and we would never detect this effect. So we're very, very lucky that we have a useful moon. By the way, this is a picture taken from the space station during the 2017 eclipse. This is what you see. You see this fuzzy blob on the ground, the shadow of the moon. Here's a picture taken the day of the eclipse in 2017 from a spacecraft called SOHO, a solar observer. And you see these sunspots. And I know it's a little hard to tell. I'm going to show you a better picture. My grandson took this picture from our spot in Wyoming during the eclipse from the ground using a cheap camera. I think you can see the little blurry spots here. Here's what the picture he took. And you can see the sunspots. These are from the pictures he took using my camera, and this is what you see from the SOHO spacecraft. So a $300 camera is good enough to detect this kind of effect these days. And this is what we saw on the cruise ship as the moon began to cross the disk of the sun. Oh, no, this is 2017, sorry. Sunspots, here's a couple more sunspots, and this is, of course, the moon starting to make its crossing of the disk of the sun. Here is what we saw in the annular eclipse.
How cool is that?
On the day after Christmas, I took this picture. This is the most famous picture taken at the time by this photographer. He was on the shore in Qatar, and there's the rising sun. This eclipse occurred during sunrise, and that is the moon blocking it out. So you call this the devil's horns. Now, just 3 days ago, we had a similar eclipse, curiously, almost the same trajectory on Earth from Central Africa to the Southeast Asia, passing right through. This is where we were in December, but here's another eclipse, June 21st, 2020, an annular eclipse, and here you see Baily's beads. These are caused by the fact that the moon is not a smooth sphere. It's got surface topography.
I was wondering about that.
Now, let's talk about applications. I mentioned earlier that everybody in 1919 assumed that Einstein's theory was useless, and that is not true. GPS, we all have it in our phones or our cars. It does not work unless you use Einstein's theory. And the reason is the satellite, each of the GPS satellites carries a very accurate atomic clock. That clock runs at a different rate when it's out in space than it did when it was on Earth. Because it's on Earth, it's close to a gravitational body, namely our planet. And as the satellite takes it out to its orbit, the rate at which the clock progresses speeds up. So there has to be an adjustment made to the clock in your phone and the clock on GPS. Otherwise, GPS would have error rates on a scale of 5 to 7 miles per day. And that's not particularly useful if you're looking for the nearest Pizza Hut. The difference, by the way, the difference in progress per day between the clock on the GPS satellite and the clock here on Earth is 39 billionths of a second, which doesn't sound like much, but it matters a lot. And anybody want to contact me, I have a lecture on how you calculate this little tiny difference. So that's a GPS receiver that a surveyor might use. Now, I want to show you something really extraordinary. It's called a centimeter clock. An international team, including people here in the nearby town of Boulder, Colorado, managed to build a clock so accurate that moving the clock by 1 centimeter vertically in Earth's gravitational field produces a detectable effect. And to get this kind of sensitivity, you need a clock that's stable on this scale, 1 second every 200 million years. Us oldsters remember John Cameron Swayze bragging about Timex watches. The Timex watch was good to, I don't know, 1 second per month. This is 1 second every 200 million years. And with that sensitivity, you can detect a motion, vertical motion of this clock assembly by 1 centimeter. That's called a 1 centimeter clock. I'm going to just show pictures for a minute. I just want to open the microphone for questions as we're starting to run out of time. Gravitational waves, a direct result of Einstein's theory. We now have gravitational wave sensors. Various other kinds of proof. And I'm going to share this slide deck with Bruce, so if others want it, they can have it and present it to others if they care to. Oh, and this is fun. This is, you're about to see measurements of the trajectories of stars near the center of our Milky Way galaxy, taken over a period of about almost 20 years, showing that stars that pass near the center of the galaxy are in these elliptic orbits because there's a massive black hole right there. We did not see the black hole, but we see the influence it has on the space-time near the orbits of these stars, and we can see these elliptical orbits. Here they are depicted in a static image. And there are the references, and with that, Bruce, I will turn it back over to you. Stop sharing.
Well, I think we ought to ask for questions.
Absolutely.
You can unmute yourself now. I think I got everybody to the point where if you choose to, you can unmute yourself if you have a question for Ed.
So the eternal question is, did Einstein really perceive this and then make the math, come up with the mathematics, or were the mathematics first and then he came out with his theories?
The answer is, in the early days, he thought about these kinds of issues.
He must have thought
He
about
did what are called in German Gedanken experiments. He kept thinking and thinking and thinking, and then he realized he's got to put some math together, and he got stymied pretty quickly, and that's when Grossman stepped in and came to the rescue, because Grossman knew exactly the field of mathematics that could save the day. And that's this thing I mentioned called differential geometry, which was new. It had only been invented in the 1870s and 1880s.
So it's the same thing with a quantum mathematician. So somebody came up with the idea and then they had to invent a whole new field of mathematics to come up with it.
Right. Right. A big part of
somebody said this is.
So there had to be one, at least
really different,
right? It's like the speed. You didn't know the speed of light, right, or something.
I didn't hear the first part of your question, Bruce.
Well, he had to know something to start with, right?
Oh, right.
That's my question.
He had already confirmed, at least in thought experiments, special relativity that he introduced in 1905. But by the time he did the theory of gravity, there had been no measurements to prove the special theory, which does not involve gravity. It's all about how things behave if you're going near the speed of light, and nobody was doing those sort of things. Nowadays, a college freshman does experiments with cosmic rays and proves that special relativity works, because they measure the lifetime of particles that in the laboratory last hundreds of nanoseconds, but they survive an entire trip through our atmosphere because their clock is slowed down because they're going so fast. So,
But did he come up with that in his mind before the mathematics, or did he do the mathematics first?
are you talking about the special theory?
Any of it. I've always wondered about that.
So it was a convergence of
proved
ideas.
But did
He did not do the math first on gravity. He had the concepts in mind. He began doing the math, and as I say, he got stumped, and he and Grossman worked for 2 years to work out the mathematics.
Okay.
Because I think that's even cooler. I mean, how could you just have an idea and then make up the math? I mean, Schrodinger and all those guys did the same thing. Schrodinger came up with field theory and all this sort of stuff. They had the idea in the mind. They came up with that.
Yeah. Well, there's a great book by Walter Isaacson on Einstein that's not technical, and it has maybe 2 chapters on this progression of or maturation of his theory. So if you're interested in reading more about the history, there are many, many histories of Einstein. Isaacson's is very good. And there's one by Abraham Pais, P-A-I-S, that's excellent. He was actually a colleague of Einstein's and has a very, very technical discussion of Einstein's progression from 1905 till 1920 or so.
Ed. So Ed, sorry.
Yes.
What do you know about Schwarzschild and how he
Yeah.
looked at the theories of relativity and then came up with his own idea about the Schwarzschild radius?
There's a astonishing story of how quickly people were able to digest Einstein's theory and produce results. And what my friend Dave Crowder is talking about is Schwarzschild used the equation to calculate various projections of how the universe will unfold based on Einstein's theory. This was done within, 10 or 12 months of the theory becoming available to people. And Schwarzschild produced a result which people are still using today. It's used to calculate the properties of black holes and so forth. And Einstein actually wrote letters about how amazed he was that people could digest this very complicated theory and produce results. And Schwarzschild was right there. Unfortunately, he died. He was an artillery soldier in the Great War, and was injured and then became sick and died. Another very important player is Lemaitre, who was a priest trained in astronomy. And Lemaitre and a few others, including a guy named Friedman, produced an even more refined theory of how Einstein's theory of gravity could be used to calculate how the universe would evolve. So the contributions came right away. Now, as I say, we have an application in GPS. It took until the mid-50s before that idea became something that people took seriously, and the US Navy developed experiments. I was fortunate, actually, Steve Mudrick, who's on the screen, and I were students at the University of Maryland in the early 60s, and Joe Weber was a faculty member there trying to detect gravitational waves as early as like 1962 to 65. It took until very recently. We now have the big gravitational wave sensors that I briefly showed on the screen. And successfully now we have a new window on the universe because we can detect mergers of massive objects using gravitational waves that are predicted by Einstein's theory.
Ed, you said that he started out with the speed of light being the maximum speed in the universe. Now, how did he come to that conclusion?
Well, yeah, okay. So I have been fortunate enough to be in Bern, Switzerland, and stood in front of Einstein's house. And if you look up the hill from Einstein's house, you see the railroad station. And on the top of the railroad station is a big tower with a clock. And the story goes that Einstein used to, on his way to the university or the patent office every day, he would look at that clock and think about, I wonder what it's like to travel with a light ray. If I stood next to a light ray, what would my clock look like? If I'm going at the speed of light, I'm keeping up. And he realized that that doesn't work. And there's other reasons that have to do with Maxwell's theory of electromagnetism, which was only 20 years old when Einstein was doing his work, where he realized different observers will all see the speed of light as being the same. For example, if you shoot a bullet at another gun and the two bullets collide, the relative velocity of those two bullets is the addition of their velocities. That's not true for light. If you're traveling near the speed of light toward somebody else and they shoot a light beam at you, you do not see that light beam coming at you at twice the speed of light. It doesn't work that way. And the algebra, there's only algebra required to get that result. So,
didn't the Michelson-Morley experiment
yes.
Happen before he
Right.
had come up with his, okay.
Yeah.
Well, yes. So in the 1880s, Michelson and Morley, who were in Cleveland doing experiments, and at the time, the theory of how light propagated was the universe was filled with something like a fluid or vapor called the ether. And Michelson and Morley realized they could test whether there was an ether by making measurements of the apparent motion of Earth relative to astronomical objects at 6-month intervals. So at one time, the planet was going away from you, another time the planets are coming towards you. And they did optical experiments and could not detect the presence of the ether. That was a factor. Ernst Mach, whose name is associated with high-speed aircraft, he had also written in a more philosophical way about the speed of light and Newton's idea that the universe is a fixed volume that never changes. That is, there's a grid, a kind of an imaginary grid in which everything moves. The idea of how that grid could be altered in shape was something that Mach had speculated about in a philosophical sense. So there was a lot of stuff floating around Einstein as he developed these ideas, and they were all disparate. Nobody really understood, but by 1905, Einstein figured out the special theory, and that was the foundation for the general theory of relativity that we now call the theory of gravity.
Well, you know what, Ed? I think you're going to have to do another talk because that was really good.
That was good.
Thank you. I have one in mind, which I'll correspond with Bruce about to see if he thinks it's worthy. But I'm grateful I had a big interested audience, and happy to come back and give another talk.
Yeah, this could be the theory of zero. We've been, last week was 28, this week is 34 people, and who knows? It could go to infinity.
Exponential growth, but pretty soon you're going to get a call from the people at Zoom saying, cut it out. You're constraining our system.
100.
Yeah,
all right.
that's right.
I have a couple of little questions. First of all, we were informed of this from the Long Island engineers group. Is anybody else here from Long Island, and did they get it from the engineers group?
Yeah, I hear. Oh, we did.
Okay, good. And I have a question about one of your slides. You showed a picture of an eclipse, and you gave it some name, and there was the red and the circle of the moon coming down, and it looked like it was right over the surface of the Earth. And there was another dark area at the bottom, opposite the sun coming in, and I wondered what that was.
Well, let's go back to the slides.
Okay.
And I will.
Someone has a radio on.
Yeah, somebody's making noise here.
Yeah, so maybe you can, here's what we'll do. I don't know your name, but you're sitting next to Judy.
Yeah, I'm Dave.
Oh, okay, Dave. Let's do this. I'm going to share.
I'm going to mute everybody on account of that dog, so here you go.
Yeah,
Okay, that's the one I think. That's
so
where-
Dave, I'm going to share my screen. Here's what we do. Oh, I have an idea. All right, so Dave, yell out when you see the one that you're interested in. I'm going backwards through the presentation.
There we go.
Okay. Yeah, you passed it.
But we were muted.
Yeah.
Okay,
So go back again.
all right,
No.
so
Do I remember where it was?
You'll. No.
Wait a minute. Oh, gosh.
This is, yeah.
Yeah.
No, it was bad.
let's do this, Dave.
Never
No,
mind.
don't worry.
Well, I'm gonna go back. I'm determined that you
It was
get
on your
satisfaction.
Easter trip. It was like in Kuwait.
Okay, so here's what I'm gonna do, Dave. I'm now gonna
Oh,
show
okay.
you lots of slides. If you see it, you shout out, and I will stop and we'll zoom in on it.
You're ready. This is sunspots.
There it is. Number 30.
Number 30. Yes, sir.
Yes.
Okay. What's your question?
All right. I can see the moon, the
With the horn.
dark circle,
Yeah.
but what is this little circle under it?
In the horn.
Oh, here.
Yeah,
Yes.
You're,
right there.
you're talking about that? Oh, yes. That's a refraction because the sun is rising and the light rays from the sun are skimming over the ocean. And there's humidity and air turbulence, and the light rays from the sun are deflected away from you. So if you're standing on the beach where Elias, the photographer, was standing, you don't actually see the sun. Those rays are above your head or in the ocean. Some of you may have seen or experienced a blue flash. I wonder if anybody has experienced
The green flash.
or the green flash. There's two of them.
Yeah.
And this is related to the same thing. If you're standing on the beach during sunrise or sunset, you will see this optical effect due to the atmospheric refraction that either projects the light down into the ocean or projects it above your head, and you don't see any light there.
This is the sun. All
Yeah,
right,
this
thank
is-
you very much.
Yeah, that's the sun, and this is the moon right here.
Yeah.
Yeah.
And you can see Elias was lucky that this boat didn't get in the way.
Yeah, I know. That would have been terrible. I'm going to end the call Because
Yes,
we do try to keep it down, close to an hour here.
yeah,
And this way, we've whetted your appetite. So the next time that Ed does a talk, you will come back. You won't have been saturated. So we have scheduled all the way through the month of July, and we have room for new speakers in August. So if anybody has something that you're dying to tell us about, like I think Roger Reese could talk about computer chips and Intel, and we'd look forward to that, for instance. Anyway, thank you very much for attending Science to the Board today, and have a nice week, and see you next Wednesday. If you don't have my email, yeah.
Thank you.
Thank you. Get it to Ed or somebody that you know, and or send it to me if you can find me. Thank you.
okay, good night, everybody.
Night. Thank you.
Bye.
Hey, Dave.
Good night.